When we observe heavy machinery in motion, like a bullet train accelerating, we are watching the macroscopic result of billions of invisible atomic interactions. In physics, any movement requires a force. A force is strictly defined as a push or a pull capable of changing an object's shape, its speed, or its direction. Most forces we experience are contact forces, which require physical friction to transfer energy. But certain forces operate across empty space without any physical contact. Magnetism is one of these non-contact forces. It exerts physical pushes and pulls through an invisible region of space called a magnetic field. Every permanent magnet operates on absolute geometric rules. Magnetic field lines consistently flow from the North Pole to the South Pole. If you bring two identical poles together, they repel. Bring opposite poles together, and they attract. Magnetism functions as an invisible spatial field, providing the physical foundation for nearly every mechanical system in the modern world. In 1820, physicist Hans Christian Ørsted observed a compass needle deflect when placed near a current-carrying wire. He discovered that a flowing electric current intrinsically generates its own circular magnetic field. Physicists use the right-hand grip rule. Point your right thumb in the upward current's direction, and your curling fingers map the magnetic field's rotation. In 2D notation, a dot represents current moving toward you, and a cross represents current moving away. The right-hand grip rule relies strictly on conventional current, which dictates that charge flows from positive to negative. While actual electrons flow the opposite way, the mathematical convention remains consistent for mapping the field. Recognizing electricity and magnetism as two expressions of the same phenomenon gives us the ability to artificially synthesize and control magnetic fields. A single straight wire generates a radial magnetic field, but that field is too diffuse to perform heavy mechanical work. By coiling the wire into tight loops, those individual circular fields physically intersect. Opposing vectors on the outside cancel out. Inside, the vectors align and compound straight down the center, creating a uniform field. This specific coiled structure is called a solenoid. To determine the poles of a solenoid, we look at the face of the coil. If the current flows anticlockwise, that end acts as the North Pole. If it flows clockwise, it is the South Pole. To upgrade a standard solenoid into a true electromagnet, we insert a soft iron cord directly into the center of the coil. Iron has high magnetic permeability. It catches the solenoid's magnetic field and magnetizes temporarily, multiplying the overall field strength. Unlike permanent magnets, electromagnets can be switched on and off instantly. Their polarity can be reversed by flipping the current, and their strength can be scaled by adjusting the current or the number of wire turns. This simple architecture is highly scalable. Large coils and massive currents allow industrial scrapyard cranes to lift entire cars with a single toggle switch. By altering the physical geometry of a wire and adding an iron core, we successfully engineer highly concentrated, controllable magnetic power. This synthetic magnetic field provides a method for generating mechanical thrust. We achieve this by forcing the wire's field to physically collide with an external, permanent magnetic field. Placed between magnetic poles, the wire's field interacts with the external field. Above the wire, fields align in the same direction, creating dense, constructive interference. Below, they oppose and cancel out, creating a weak field. This spatial gradient produces a physical push, the motor effect. To predict the precise three-dimensional direction of this force, physicists use Fleming's left-hand rule. Hold your left hand with 3 fingers at right angles. The index finger points toward the external magnetic field. The middle finger points in the direction of conventional current. Your thumb then points in the direction of the resulting mechanical motion. The exact thrust generated by this interaction is governed by the equation F equals B times I times L. Force equals the magnetic field strength in Teslas, multiplied by the current in amperes, multiplied by the length of the conductor. Doubling any one of these variables exactly doubles the physical thrust. We have now translated an invisible electromagnetic field into predictable, mathematically precise mechanical motion. A straight wire produces a single linear push. To achieve continuous rotation, we bend the wire into a rectangular loop and place it between the permanent magnetic poles. Current flows down one side of the loop and up the other. Because the current directions are reversed, the motor effect pushes the left side of the coil up while pushing the right side down. This creates a torque that spins the coil. Once the loop rotates 180 degrees, the sides swap positions. The force vectors would immediately reverse and push the coil backward, stopping rotation. The solution is a split ring commutator. This device connects the coil to the power supply, breaking contact and reconnecting every half turn. By reversing the current in the coil exactly as it flips over, the commutator ensures the motor effect always applies a constant turning force in one continuous direction. This specific arrangement of coils, fields, and commutators defines the core architecture of every electric motor in use today. In the 1830s, Michael Faraday tested a rigorous hypothesis. If electricity can induce mechanical motion should also induce electricity. He proved this through electromagnetic induction. By forcing a conductor through a magnetic field, you generate a voltage across the wire. This strictly requires relative motion. Either the wire must physically cut through the magnetic field lines, or the magnetic field must physically move across the wire. The voltage induced across the wire scales precisely. You can amplify it by increasing the speed of the movement, utilizing the stronger magnetic field, or adding more turns to the coil. This is the exact inverse of the electric motor. Applying physical rotation to a coil inside a magnetic field generates current, a principle that scales from small bicycle dynamos to massive industrial infrastructure. The universe is perfectly symmetrical. We can consume power to create motion, or harvest ambient mechanical motion to generate power. This leads to a final mechanical question. Can we utilize electromagnetic induction to transfer power between two separate circuits without any moving parts? We can, using a transformer. A transformer consists of a primary coil and a secondary coil, wound around opposite sides of a shared square iron core. The two coils do not physically touch. By pushing an alternating current into the primary coil, we generate a magnetic field. Because the current alternates, this field constantly expands, collapses, and reverses direction inside the iron core. As this shifting magnetic field continually sweeps across the stationary secondary coil, it acts exactly like physical movement, inducing a new, continuous voltage in the second circuit. The output is dictated by a strict ratio. The primary voltage divided by the secondary voltage is perfectly equal to the number of turns on the primary coil divided by the turns on the secondary coil. Power grids utilize step-up transformers, which have more turns on the secondary coil, to push high-voltage electricity across vast distances with minimal energy loss. When electricity reaches a residential area, step-down transformers reverse the ratio, reducing the voltage down to safe household levels before it reaches a wall outlet. From the right-hand grip rule of a single electron, up to the massive transformers powering global civilization, all electrical infrastructure relies entirely on the geometric manipulation of one perfectly symmetrical, invisible force.